Hey everyone, and welcome to this explainer brought to you by Forge College. So if you hung out with us for our last session, you know we were deep in the weeds reviewing Solana program template structures. We mapped out exactly where our instruction arguments live and where the client constructs those instructions. Well, today we're taking the next big step in programming with Solana. We are diving into customizing input parameters. Basically, we're going to learn how to safely modify that code without, completely blowing up our programs. Because let's be real here, absolutely nothing ruins a dev's day quite like a catastrophic on-chain deserialization error.
Here is the quick blueprint for today's explainer. We'll start with the client program contract, move on to the anatomy of input parameters, and then look at a real-world example of adding deadlines. After that, we'll tackle backward compatibility, look at some AI-assisted coding scaffolds, and finally wrap things up with some next steps. All right, let's jump right into Section 1, the client program contract, focusing on the serialization API. I really want you to think of input parameters as a legally binding, completely unforgiving contract between your off-chain client and your on-chain Solana program. The ultimate bottleneck of this whole operation? It's deserialization. See, the client sends over this raw byte buffer. The Solana program then has to take those serialized instruction data bytes and convert them into typed arguments. And listen, the blockchain does not care about your feelings. If your client sends over a 32-bit integer, but your program is sitting there expecting a 64-bit integer, yeah, that translation fails catastrophically. The contract is breached, and your program just halts. Game over. It's like a giant puzzle where every piece has to fit perfectly. On the program side, you have these very strict Rust and Anchor structs. Over on the client side, your payloads are probably written in TypeScript. Both of these sides must perfectly align. I'm talking the exact field order, the exact data length, and the exact type. To put that into perspective, imagine you accidentally swap the order of an amount field and a timestamp field in your TypeScript client. Your Rust program is going to happily read that massive timestamp as the token amount, and suddenly you're trying to transfer 3 billion tokens instead of 10. So yeah, alignment is literally everything. Moving on to Section 2, Anatomy of Input Parameters, looking at our data flow architecture. Let's actually draft up the blueprints for the data flowing through this serialization tube. We've got 4 distinct parameter categories here. For a required numeric, you're usually looking at a standard U64 in Rust. The client must always provide it, and you'll definitely want to validate that it's non-zero. For an optional numeric, Rust uses an option wrapper, which is super handy because it means the client can actually omit it if they want. Then we have short text. This one is tricky because it requires strict max length validations. Why? Because storing huge strings on chain can get expensive really fast. Finally, feature toggles just use simple booleans. The key takeaway here? Every single data type requires its own specific Rust representation, client handling method, and validation strategy. Now, deserialization just converts the bytes to get them through the front door. But validation is the bouncer that actually enforces the strict business rules. And here is the golden rule. You must enforce these rules before mutating any state. Think about it. If you change an account balance and then realize the input was actually invalid, you've just left your program in a corrupted mess. No thanks. So validate first. Also, keep your logic deterministic and computationally cheap to save on compute units. Oh, and please, for the love of your front-end team, use explicit Anchor error codes. Returning a generic error 0 is going to make debugging an absolute nightmare for them. All right, Section 3, let's look at a real-world scenario, adding deadlines. So what does this actually look like in practice? Imagine we want to add a strict time constraint to a token transfer instruction. Step 1, we crack open our Rust argument struct, and we add a brand new field, deadline, as a U64. Step 2, we jump inside our instruction handler. Here, we write validation logic to pull Solana's clock sysvar, and we check if our deadline is greater than the current clock.unix timestamp. If time has run out, boom, we throw a custom error. And then, step 3, we hop over to our TypeScript client and update the instruction payload so it passes this new deadline. You have to update both sides simultaneously, or the whole thing breaks. Which leads us perfectly into Section 4, backward compatibility, or how to avoid stranding your users. Okay, but wait. What happens if you deploy this awesome new required deadline field to the blockchain, but some of your users haven't refreshed their browser, and they're still using an older version of your client app? Well, if you just slam a newly required field into your on-chain struct, those old clients are going to send the old byte buffer, and it will instantly break. Deserialization fails.
Suddenly, your users are stranded out in the digital wilderness, furiously refreshing their apps and getting transaction errors. We absolutely have to employ pragmatic strategies to prevent this from happening.
Luckily, the elegant engineering solution here is twofold. First, instead of a strictly required U64, you can wrap it in the Rust option enum to make it genuinely optional. Or you can use what we call a Sentinel default value. For example, you could say that if the deadline is passed simply as a 0, your program logic knows to treat that as no deadline applied. By defaulting to a clearly documented Sentinel value, or just making it an optional parameter, those older clients can keep interacting with your program completely uninterrupted while you take your time gradually rolling out the front-end updates. Much smoother, right?
Section 5. AI-assisted coding scaffolds. Let's talk about vibe coding tasks. Now, I know exactly what you're thinking. Man, writing all these structs and meticulously aligning TypeScript sounds kind of tedious. And hey, you're right, for sure. AI is fantastic for this kind of repetitive scaffolding. But remember, you are still the lead engineer here. Step 1, give the AI a highly focused prompt. Step 2, don't just blindly paste it. Inspect the output. Do the field names actually match? Are the anchor error codes correct? Step 3, and this is absolutely crucial, run local validation. Compile it using cargo build BPF. If it fails, feed that error right back to the AI. Finally, step 4, iterate and harden your tests. Let the AI build the frame, but you gotta verify the structural integrity. All right, let's bring it home with Section 6, wrap up and next steps, locking in these blueprints. We have covered a massive amount of ground today, so here is your quick recap to really lock this in. First, always perfectly align your field types in order between the client and the program. Second, validate early, validate often, and use those explicit error codes. Third, preserve backward compatibility by using the Rust option enum or safe Sentinel values. And finally, test your changes locally. The absolute biggest takeaway I want you to have is that any parameter change is basically a two-front war. It requires simultaneous updates in both your program code and your client code. I want to leave you with this one final thought. Treat parameter changes as an API evolution. Your smart contract program might be completely ready for the future, but are your clients ready for your program? It's an ongoing relationship, and it requires some really careful management. If you want to dive deeper into this, learn how to run your own local validator, or just master Solana development and other Web3 topics, you absolutely need to visit forge.college today. Thanks so much for joining me on this explainer by Forge College, and I will see you in the next one, where we start modifying the actual overarching program logic. See ya!